Well, so we're going to talk about streaming analytics. We're going to talk about a framework for doing this particular kind of streaming analytic. Hopefully I will have motivated why one would want to do this. And then you'll see a demo, right? So my name's Casey Sella. I'm an engineer at Hortonworks. I'm part of the Apache Metron team. We just got our 0.1 beta release out last night. Did it from a hotel room. Rock on Metron. I used to be a data scientist. I am a data scientist on the team. I was a data scientist in the field at Hortonworks, so I've seen a lot of data science use cases. And before that, I worked in medical informatics, which you'll see from the demo that I'm a little bit biased toward medical data. And before that, I was a graduate student, so that was fun too. All right, so a few assertions that may or may not be widely accepted, but I think are true and what motivated this talk. I believe that the future really does involve non-trivial analytics done on streaming data. The focus there is on non-trivial. Right, up until this point, and we saw the same thing happen with Hadoop when it was just starting to get adopted. Right, I saw so many word count examples. I swear I could do word count in my sleep at this point from MapReduce. Right, we're seeing a similar kind of thing going on with streaming. Everyone realizes that we're getting streaming data. We've had Storm for a long time. By the way, props to the Storm team for 1.0 release. It's awesome too. We've had Storm for some time. We're not really seeing the sort of streaming analytics come on board. So I began to wonder to myself, like, what's kind of the horizontal use case here? Right, is there an analytic that cross-cuts a lot of different domains? And so from the field, one that kind of comes, there's one that sort of comes to mind, and it's anomaly detection or outlier analysis. So the other thing I want to point out is this is not just IoT. IoT is kind of why we're talking about this now, because there's going to be a ton of data and it's sensor data, but we've had a lot of streaming data. So hopefully this is going to motivate. So the demos are going to be two demos. One of them is going to be sort of your traditional IoT demo. We have a temperature sensor. The other one is going to actually be more of a fraud analytics use case that I have done in the past in batch, but I think could be and should be done as data flows by, right? Because at any rate. So, and that's because the reason why you want to do that, you want to transform that batch model into a streaming model, is because you really need insights to keep pace with the velocity of your data. As data's coming by, you want to know the outliers then, or at least like an hour behind, or a day behind, or something like that, not a year behind, right? You don't want to wait till everything is in. Okay, so there's good and bad here. The good, lots of data can be coerced into a time series. So you have a nice consistent, structure, right? So for those of you who don't know, a time series is a set of points that have a timestamp attached to them. So think of like a stock ticker as a classical example of a time series. The problem is there's a lot of data, and it comes at you very, very fast. And it's not just that you're doing this for one. So a nice example of a time series would be like a temperature sensor. You generally don't have just like one sensor. You have a smart factory with a lot of sensors. So one of the motivating examples of this was when I was in the field, a junior data scientist got a problem tasked to him, and it was an energy company. And they said, yeah, look, here's a bunch of sensor data for this plant, and it's the plant had a failure at this point. We really want to know what happened leading up to that failure. What sensors should we be monitoring? So this is a common ask, right? We want to know, we want the computer, we want the streaming algorithm, we want the data scientists to help us figure out what should we be looking at, what should the humans be looking at to increase the signal to noise ratio so that they're less likely, so they can push the big red button and say plant shut down because we don't want something to blow up, right? Blowing up is bad, turns out. And this is really the killer app, I think. It's a nice horizontal use case. So, but the problem with it is it's really computationally intensive. So February 2015, Netflix had a really great blog post, and they open sourced a project called Netflix Suros. Who here has heard of that? No one's heard of it other than me because I'm a nerd and data scientist, right? But I'd seen this in the field, and what they did was they said, hey, we have this great outlier detection algorithm. It's using robust PCA. It's not specific to a given distribution, which is what I was looking for. I was like, this is great, and it's written in Pig, and it's great. And then you begin to run it, and you realize like it takes forever to run. You're like, oh, this isn't great. So then, sure enough, like 3 or 4 months later, they released another blog post about outlier detection. Say, hey, look, here's another way to do it, but it's not as accurate as this, but it works well for our streaming data. And I began to think, that's not ideal. I want the best of both worlds. I want it to be fast, and I want it to also, I want it to scale, and I want it to be like super robust and not specific to distribution. So I began thinking on the problem. And there's no real shortage of computational frameworks to handle streaming, right? We have Storm, we have Flink, we have Spark streaming, right? There's no shortage of that infrastructure there, but there's a real lack of high quality frameworks for doing this outlier detection. And I realize the reason why this is the case is because you really kind of have to think about this in a different way. So what this is, in more formal footing, is it's an analytical technique which interesting points can be differentiated from normal points. You'll notice those quotes, because interesting and normal are kind of hard to define mathematically. It's kind of hard to do. Generally, interesting often implies some sort of error state or some sort of fraud, right? Or some sort of temperature has gone out of whack. So recently, they beat me to this because there's some guys at MIT and Stanford. They did a joint project with Cambridge Mobile Telematics, and they constructed a very similar system to what you're going to see, but it's different in some important ways, and I'll talk about that at the end to differentiate. Most specifically, they were focused on how much data can they pump through one node. This is a distributed system, right? So what they noted in this is that data produced by a lot of the IoT applications often have some form, they fit some sort of ordinary distribution, not necessarily normal, right? But some ordinary distribution. The other thing that you'll note is IoT anomalies are often systemic, right? So failures in this sensor can correlate to failures in that sensor. And it often just correlates to just a plummet, right? The system crashes or whatever. And they're often fairly rare. So we'll talk about the hybrid approach that I've come up with here that I think works quite well. So for the function of scale, we really need a two-phase approach. The first phase, for every data point, you want to detect the outliers using a robust estimator, right? Something that's fairly simple, but uses something like distributional sketching. So distributional sketching, for those who don't know, is an approximation. Like for the example that's being used here is Q-trees. So it's an approximation of the distribution of values. So for your window, you get an approximation. And that, in and of itself, allows you to do, it opens up the ability to do things like use median absolute deviation, which we'll go over a little bit. But once you have that data, you also gather together a sample that's biased by recency. So you want recent data to be more likely to be in your window, in your window sample than non-recent data. So once you have the candidates here done through this, that's been given to you through the computationally advantageous or much simpler algorithm from a computational perspective, using the distributional sketches, then you can pass the sample into the more traditional outlier analysis algorithm, like robust PCA, right? So specifically, what I've created is the framework to allow you to plug in those two things with an implementation with a kind of a default implementation for those guys. So the robust PCA implementation might be expensive computationally, but it's run so infrequently that you can still meet your scalability requirements. So the only outliers that really get shown are the ones who pass both filters. So what you want is a relatively loose first filter and a fairly tight second filter in general. You don't want to do every point, right? You don't want to pass every point to the really computationally intense portion, but you also want to pass enough so that you have some leeway for the stuff that isn't detected with just median absolute deviation, right? And that's still a bit of an art, but it's at least possible now. So now this fits within a storm bolt. It's a plain Java program that can fit inside of your Spark streaming. It can fit inside of Flink. It can fit inside of NiFi, right? So you don't have to have like multiple nodes and worry about passing data between. This fits in nice one bolt inside a storm, for instance, with deterministic space and relatively deterministic computation, because presumably the outliers are relatively infrequent. Right? So it becomes your data filter. And that's the way to think of outlier detection. You want it to be a data filter that you put right in front of the fire hose so that you only get the filter results, right? And those can be reported up for a human to look at, or for downstream processing to look at, right? So these things can be composed. Okay, so we'll talk briefly about median and absolute deviation. I know this is in the streaming section of the talk, so I'm not gonna bore you guys with too much data science. There is actual math involved here, so for anyone who wants to avert their eyes, you're welcome to. You can understand the talk without knowing necessarily what this is. So the idea is that it's a robust statistic. When most people think about what I've noticed in the field is a lot of people are deciding that outlier analysis is really just thresholding, right? It's, well, if it's above this point and lower than this point, then I want to say it's an outlier, right? But that's not as nice, right? Because it may be an outlier, or what a nicer way to think about this is you really want something that deviates from your distribution. Right? If something is steadily going up, right, just because it hits your threshold, it's hard to create that threshold. If something is going up and all of a sudden the first derivative jumps up here, like, yeah, that's a definite outlier, right? But you want it to be, outliers really should be considered in terms of distribution, not in terms of absolute values, right? That's the way to think about it. So it's a robust statistic. So what a robust statistic is it gives good performance from data drawn from a wide variety of distributions. And the macro-based guys also, they use this as one of their primary outlier analysis techniques. It works quite well with real data, is the thing that I've noticed. So when we talked about the energy company example, or the energy factor example, or the power plant example, this is what we used on the individual sensors. Right? So unlike a standard mean/standard deviation combo type thing, where if it's more than 6 sigmas away or something like that, this is not as sensitive to outliers. So it's a bit more lenient when it comes to that. So it works quite well with real data. So really the idea behind this is you want to get this notion of the median absolute deviation. So it's the deviation of every point from the median, right? But that means you have to compute the median. And if you remember, if you remember how to compute a median, that generally involves sorting data. That's where the distributional sketching comes in. You can get the percentile from the distributional sketch in constant time, right? That's the real key. That's the real hook here, because this is not necessarily nice computationally if you do it without the sketching. Okay. So in particular, a point's considered an outlier if its distance is more than some z-score, which is computed. There's a threshold. One of the hard things is figuring out the threshold, actually. So one of the things that I actually did in this was, and I found this works in the field quite well, is instead of giving a fixed threshold, if this z-score is over like 3.5 or whatever, which is the traditional threshold for an outlier, I've noticed in a lot of data that's not necessarily true. What I did was I said, look, I'm going to keep the distribution of the z-scores too. I'm going to say if it's more than the 95th percentile of the past, Windows z-scores, then I'll consider that an outlier, and that gives a nice smoothing to it. But anyway, so the TLDR is a formal way. It's a formal way to encode our intuition. If a point's far away from some notion of what's normal, like the central point, then it's likely an outlier. So relatively simple. So we'll talk about the demos now, because those are the more fun anyway. That's why everyone came. People love demos. Hopefully you'll like this one. So this is the architecture. Really, really simple, right? You push your data into Kafka. From the Kafka spout, you have a single outlier bolt. So keep in mind, this is Storm, but this could easily be Spark Streaming, it could easily be NiFi, it could easily be Flink, right? And from there, you push the time series data to OpenTSDB, which is a great scalable platform based on Hadoop, or based on Apache HBase to capture time series data. And the nice thing about it is a lot of the time series UI, open source time series UI tooling have support for OpenTSDB. I can't praise OpenTSDB enough. It's really great tech. From there, the outliers come out, much lower velocity data, right? So imagine the time series is high velocity data. The outliers, low velocity data. And that's getting indexed inside of Elasticsearch. Why I choose Elasticsearch? I could have chosen Solr, I could have chosen a relational database for that matter. Because the point is, that filter is splitting the stream. That's the stuff I care about, that's the context. And that's going in and getting merged inside of Grafana for our user interface. Okay? So, this is what it looks like. Okay, that's what it looks like. This is an extremely sick machine. This is it's actually quite hard to find good IoT data, IoT time series data. If someone has a really good source of IoT time series data from like real data, please let me know. That is reasonably high velocity, not super high necessarily, but reasonably high velocity. Anyway, this was pulled from an anomaly detection benchmark data set that I found online from Numenta. So I don't know what this machine does, unfortunately, but I know that it is sick. So you can see that it's all kinds of scattering all over the place here. And you'll notice that the temperature spikes here, and that eventually leads to the machine being brought down, right? And it comes back up, and it goes through its paces, right? And there's some dips in which a human probably should be interested in this. Right, so you'll see the points, but think of them not as individual points, but as clusters. And they're going to persist for the length of time in which you should be concerned, right, as a human. There are a lot of points. You can kind of winnow those down to the most important ones because you get the outlier score here, so you can further filter. Right, so the higher this value, the more of an outlier that it is, right? So here, and because we're capturing all these distributional statistics, we're also capturing the distributional statistics of the window here, so I can look at it and get my intuition. So the 50th percentile here is 92 degrees. It's at 97, right? That's somewhere between the 95th and 99th percentile, right? That's all bubbled up to the top for you. And you can do things like slice and dice. So it goes along. It's not very happy here, but it continues to go along. And it starts to do really erratic things around here. So you notice these are things that you would not have picked up necessarily if you did simple thresholding, right? Because this is an okay temperature, right? So a simple threshold isn't going to show that. What you really want is when it starts to shake, right? When it starts to have flux, which is starting here, and then it dips, and then it goes down for a crash here. So the idea is that hopefully you would have a human looking at this across your sensors, across your machines in your smart factory, and getting a sense of which machines are showing anomalous behavior. Because really, honestly, if I'm a machine operator and I'm seeing this many outlier drops, I'm talking about how we should calibrate that machine, right? So you can prevent it before it happens. You don't want the machine to crash before you react. Okay, so that's kind of the traditional IoT use case. I want to show you one that I like. So the other nice thing about this is, because it's scalable, you also can think of fraud as an outlier. So there's an open data set, a real data set, about the relationship in the US between physicians and those people who give physicians money in terms of industry, right? It's like pharmaceutical industry. So every gift that a physician gets comes into this data set. And at the end of the year, they publish this data set out. My point is, why not publish this as it goes? Because if physicians, and why not look at physicians that are being given gifts outside of the bounds of what one would consider appropriate or normal for other physicians in their specialty. So you might not want to compare a dentist to a heart surgeon. They may get different types of gifts, different distributions, right? But you might want to consider a dentist along with another dentist. So we get this one stream of data that we're splitting into many different independent time series. One per specialty and per reason, right? And we're doing the analysis on that. So the same code, same storm topology was run on both of these guys, right? So I create a little Grafana database. If I'm the person in the government in charge of looking at fraud for physicians, which I'm not, I'm looking here and I'm saying, okay, here are the outliers across all specialties. And this is ordered by the degree to which I believe it's an outlier. So you look at this first one. It's about 6.5K, right? That's lower than the second one. This osteopathic and this family medicine doctor, it's lower than the 23K given to him. But it's more of an outlier compared to his peers, is the point. So again, simple thresholding is not what you want. You want something more intelligent. Okay, so let's take a look at, so let's zoom out. It's my favorite one. The eye doctor. So we'll look at the optometrist. Look at that. Boom, right there. That's a pretty big spike, I would consider. Now, the green is her peers, or their peers. I don't know if it's her or not. I've purposely redacted the physician names. There's just a physician ID. You can get the names. I could have put the names there. Not going to do that. But the point is, you want to figure out what's the context. Is there context, right? If journalists had access to this, you could start looking at that. There was one article from the Wall Street Journal about this data set, exactly one, and it was completely forgotten, right? I'm sure there's more interesting things in this data set. So from that one outlier, you can get, again, the statistical context in which this particular outlier exists. So you can see that the 99th percentile for their peers is around $380. They were paid almost 13K. It's a lot, I would say. Wish I was getting paid that much as a gift. The other nice one, I'm cherry picking, I promise. So this person got paid. This one in particular is my favorite. Got paid 3.2K for a customer loyalty program as part of it. I don't know. I signed up for customer loyalty at my local supermarket. No one's giving me 3.5K for that. It turns out that I did this analysis in sort of in batch. Actually, there's a blog post about it on my blog, which I point out a lot of these things. And dentists get paid a lot of gifts. It turns out, right? There's lots and lots of gifts. So I can. The final one that I did want to look at was an example of how this may be reasonable to show up in this list. So we'll look at the prosthodontics. I didn't even know what that is exactly. So this person here got paid around 40K. It's a lot of money, right? But you can see they got given an implant system, a surgical implant system, right? So it's reasonable to be given this kind of thing. So it's not that just because you show up in the list, you've done something wrong. It's that a human needs to look at this, but they can't look at every point. There are thousands and hundreds of thousands of points, many doctors in the United States. What you really want to do is you want to look at just the ones that have done something outside of the norm. And that is surprisingly few, actually, it turns out, because the better your definition of normal, the fewer you're going to have. And I think that also fits well with what the macro-based guys found in IoT, is that the outliers are relatively rare. So that means that outlier analysis is, I think, a really good horizontal, cross-cutting, advanced analytic that we should be considering on our data right now. And if you're not, I think you're being left behind. Okay, any questions? I'll move to, if you want the code, it's here. It's all open source. Download it. You can run it yourself. There'll be a blog about it as well. I'll blog about it on my personal blog, and hopefully Hortonworks will too. So, any questions? And I have to give mics out if you have questions. So, I'm coming in really early. If you guys watch out, I'm going to go back and dig through that data and embarrass some more physicians. Yes. Hold on. Why don't you take the mic so it gets recorded? Thanks.
How would one of these outlier detection algorithms streaming data deal with concept drift? So
with what?
Concept drift, like the data, the machine is in a different mode, and actually the model is not even valid anymore.
Yeah. So just to repeat, actually you've spoken to the mic. So how does it deal with concept drift? So it's changed. So the idea is the machine has changed modes, right? It's all of a sudden going from the temperature. It's changed modes. The temperature is fluctuating here, and boom, it pipes up there. So the idea is that from here it'll look like. That's actually a really good question. From here it'll look like when it first bumps up modes, it'll look like a change because it's a change in distribution of values. However, as you get acclimated here, it'll stop. So it won't flap. Right? If you have thresholding, changing modes is a real problem if it's just really simple thresholding, right? Because you're just not catching those at all. So it will go up here and go and kind of flap because because it's changing distributions, but it should stop relatively soon, I would say. So again, this is the reason why. What you really want is kind of downstream, even more intelligent analytics, right, that correlate. So imagine a situation where you knew when the change in mode happens, you get the outliers, and you suppress the outliers for the first 30 minutes of the change in mode happens, right? That's not a hard thing to add to the storm topology, right? That's how you would really see this in a production system, I would say. Any other questions? Ooh, I can't see. Okay, then if you have any further questions, please don't hesitate to. Oh, there's one more. Sorry, didn't see you.
Yes, thank you. Just I have a couple of questions. Just,
sure.
For this time series data, we found we also do this some. Anomaly or outlier detection on this time series data, but we found the difficulty actually is to recognize the temporal patterns of the time series, like daily, weekly, monthly patterns. That's something deviate from the pattern that we recognize that outlier. But
so you're talking about seasonality, right?
Yeah, exactly. Some things have to incorporate some seasonal behavior inside of it.
So an intelligent choice of windows helps a lot there. That's one of the reasons why it's nice to use distributional sketching, because you can do things that are not necessarily number of point style windows, but you can do time windows. Like I could have a window of like 3 months. Like for my fraud case, it could be 3 months back that I want to keep. And that's still relatively small because that distributional sketch is tiny in terms of memory wise, right? It's just keeping a sketch. So for highly seasonal data, you're probably going to want to choose your window very intelligently. I would say you don't want to go back too far because otherwise you're going to get different patterns, essentially different modes, except naturally occurring changes in distribution. Does that answer your question?
Yeah. Okay. And one more last question is. Is this in the production or actually just for the demo case at the moment?
So this is not in production anywhere. This is. Please put it in production. It's on GitHub. Put it in production. Tell me how it goes. No, but seriously, it's on there. It has not been in production yet, but I would love to see it actually go in production. Question here.
Yeah. So in your fraud case,
I'll just repeat here. Why don't you give me that?
in your fraud case, how do you handle transactions that came in out of order? Does that affect your sketch?
Sorry, repeat the question. Would you?
So you get transactions that didn't come in the order they expected.
Oh, order. Yes. Okay, so this is one of the reasons why you want to use Kafka, right? You get some amount of order. You get some amount of order guarantees there. So if you get things out of order, then yeah, that can become difficult. However, that being said, as long as the order is not too far away, like if you get 6 months back here, then that's a problem. But if you get 3 minutes back and you have a window of 10 minutes, then because it's a distributional sketch, it doesn't require strict linearity. It just that's gonna fit into the distribution, right? That value is gonna fit into the distribution, just like any other value, as long as it lands in the same window in which it's there. But if you get it out of band, if you get something like way in the future, all of a sudden, it doesn't get put into the sketch because I don't want it to bias things, I guess, is the point. So I guess the answer is it depends. It will affect it if the order is way out of whack in terms of your window size, but it won't affect it as long as it's slightly perturbed. Make sense?
So if it's in the window, it's okay.
If it's in the window, if it's way out, it's not kosher.
But if it's just outside the window, it's what
If it's in front of the window or behind the window, it won't get included.
an hour ago when your window's 10 minutes.
Yeah, if it's an hour ago and the window's 10 minutes, then that won't get included right now. Or you have to put it inside of, or you'll have to do some pre-processing to make sure that this stuff gets put into place. But actually, that's a really big problem just in general with outlier analysis, right? Is a lot of data doesn't come in exactly exactly in the order in which you want it to. That's why you'll need to set up your Kafka queues appropriately, right? You get some order guarantees with Kafka. That's why I use Kafka here, right? You get some order guarantees, but if your data is coming in out of whack, if you actually put it in out of whack, yeah, you have to be careful with that. It's a good question, very good question. Yes, I'll repeat the question.
You were looking only at one feature like temperature,
Yes.
amount of donation. What happens now that you look at multiple features at the same time?
Right. So let me tell you a story. Real quick, I have 6 minutes to tell you a story. In that example that I gave about the energy company, right, the power plant, the first thing we started looking at, because we had all these sensors, is a huge multidimensional model. The junior data scientist, this is how I got involved in it. The junior data scientist spent a week looking at PhD theses. I said, let's just consider this individual sensors and see what that gets us. A lot of times, the individual sensors are enough. This is a solution for the individual sensors. We have not solved the multidimensional case. It could, the robust PCA approach can actually do that, right? The more computationally intensive one. But I don't know of a good distributional sketching approach that'll handle multiple dimensions. Once I find that, it'll handle multiple dimensions. How about that? But for now, I'm punting and saying it's not an important problem. No, I'm joking. It's a super important problem. We should solve it. But the technology isn't quite there that I found. Any other questions? Great questions, by the way. You guys have obviously thought about this. Who's doing outlier analysis right now? Is it working? Is it good? No, it doesn't work. No, not at all? You should use this.
Well, yeah, absolutely. But not real time.
Yeah, it's hard to do. I've seen it succeed and I've seen it fail, and a lot of it is it's quite finicky, and you have to have just the right kind of knobs.
The problem is you have to come with a very strict definition of outlier.
Yes.
That's not solving the real problem.
So I realized that this was a problem. I did a hackathon at Facebook back before I even joined Hortonworks, and it was an H-based hackathon, and I asked them because we were a startup at the time, and we were just getting killed in operational costs, right? It was just the week before I had to pull off the road to bring down some processes to avoid the name node just falling over, right? I said, how do you guys do it? How do you have so many nodes and have this work? He said, look, we capture everything inside TSDB, and my job is to look at graphs in TSDB like every morning from this time to this time. And he said, I really wish that I could have like just the important stuff bubble up. And that's how that's why I think it's an important problem. It's important for operations as well as IoT, as well as fraud. It has lots of cross-cutting concerns. Any other questions? I got 3 more minutes. Yes?
Sorry, have you ever dealt with, we can define your models, right? But your sensor can deliver the dribble in a gradual linear manner.
So it just sort of drives this way?
So you're deliberately driving it in a certain way, but there's still the outlier on either side of that.
So it's starting here, and it's just sort of deliberately being driven up, sort of just a linear function. I haven't tried that, though I would imagine that would work, right? Because you shouldn't have your distribution is shifting so slowly that it wouldn't be considered an outlier, right? Because it's at some point you're giving it a threshold. You're constructing a z-score and you're giving it a threshold, right? So that's the amount of deviation from from your sort of central point of what you consider normal. Right, so if you give that threshold far enough out, you should be able to, or you say I want z-scores that are only the 95th percentile of the previous amount of z-scores, right? Then it should handle that case fairly nicely. As you saw, it handled shifting like that, and it also handles shifting on the way up, right? If you take a look at, by the way, Grafana is really cool too. I didn't have to write a UI. No one wants me to write a UI for them at all. That's why the Metron team has people who do UI. Like, if you notice, like on the way up, even here, there's no outliers, right? Though maybe, or actually this is a better example, right? On the way down, all the way to this point, and then crash, yeah, outliers on the way down, on the hard drop. But on the way up, it's a nice gradual incline. Even though it's a gradual incline with like a sine wave in it, or some frequency component to it, right? But maybe not high frequency. Yes?
Question on the tool itself, visualization.
Yes.
Do you have multiple sensors, sensor readout on the same graph? And then
You could. So hopefully I've given the use case here where these are multiple time series being plotted, right? You get to choose the time series. I could have chosen to plot them both on the same graph, but for my purposes, it wasn't that didn't make any sense for this particular case. But you can plot multiple time series, and the tool should handle multiple time series.
could you do correlation?
So I don't think Grafana can do correlation, but I'm pretty sure the OpenTSDB UI itself can do correlation. That's actually where I'm going, where I'd like to go next with this, is automatic correlation between multiple different time series. Because that's really the killer, right? Because in IoT, you have these correlated failures. I want to find where things are correlated, right? So you can imagine, I work on Metron, which is a cybersecurity product, and I have less than a minute. Which is a cybersecurity product. This is the kind of stuff that you want to find, right? You want to detect when there's outliers and stuff. So I suspect this eventually will find its way into Metron too. All right, time's up. Thanks. Come by if you have a question.